Hello, fifth graders. This is Mr. LaBeouf, and once again, a video for early and fifth grade. And the topic of this video is clearly under the heading of symbolism. We're going to learn a piece of symbolism in math that is very prevalent. More and more you're going to see this as the years go by, many times here at St. John's before you graduate at the end of 8th grade. In 5th grade, more in 6th grade, even more in 7th and 8th grade, you're going to see the symbolism known as the exponent. And through into high school and beyond, exponents are a huge part of mathematics from now on. But like with many things in math, it's a very simple concept. Let me put forth the idea of repeated multiplication of the same number. That's what the symbolism of exponents is all about. To multiply the same number a certain number of times. Now I'm going to start with something that, I'm going to be honest with you, has become somewhat of an ongoing joke with my students beginning in 5th grade. Sometimes I'll have mischievous students who will want to try to put forth a piece of falsehood, a math lie, if you will. And a student will write this. Please don't do this, or at least please don't do it much. Maybe I'll giggle the first time you try it. But this is not a true statement. 3, the 3 with the little 2 up here does not equal 6. It does not mean 3 times 2. Which is why, if you look up above, well, let me show you how you can make this a true statement. Put a line through the equal sign. Now, the line through the equal sign means exactly what you would think it would mean if you were making the symbolism. This means not equal to. And up here, I've written a series of statements. 3 to the 2 power, that's how we read that, does not equal 2 to the 3 power. And neither one of those equals 6. Now you see something right away. Right? Not only do neither of these equal 6, but these two do not equal each other as well. So this new symbolism of exponent is not commutative. 3 with a little 2 up here is different from 2 with a little 3 up there. Now let's talk specifically about what the exponent symbolism means. I've taken the same 2 examples and now we're going to look at what they really mean. This is read as 3 to the 2 power. It can also be read as 3 squared, and we will talk in a future video about why it means 3 squared. There's a geometric reason for that. And this one down here can be read as either 2 to the 3rd power or 2 cubed. And once again, there's a geometric interpretation for why it's called cubed. And by the way, the exponent of 2 and the exponent of 3 are the only 2 that have these alternative names, squared and cubed, because our everyday experience of life in the universe is 3-dimensional. There's no 4th spatial dimension, so that's why we stop at cubed as far as the special name, the squared and the cubed. Well, this big number down here is called the base. You don't really have to remember that. I'm not going to ask you on a quiz, what is the big number called? It's the base. But just understanding how the symbolism works, this little number up here in the right corner is the exponent, also known as a power. And I will tell you in this video why they're called powers, because they're very powerful. We'll see that a little bit later. 3 to the 2 power. 2 to the 3 power. What does 3 to the 2 power mean? Well, it means take 2 3's and multiply them together. The big number here, the base, is the number that you're multiplying, and the exponent tells you how many of them to multiply. 3 to the 2 power means 3 times 3, 2 3's. And of course, that's 9. Now, 2 to the 3rd power means multiply 3 2's together. The big number is the number you're multiplying, and the exponent tells you how many of them to multiply. It's a very simple Multiply 3 2's together, 2 times 2 times 2. Now, Sometimes you have to do a little thought along the way. 3 times 3 up here was a fact that you just know it's 9, but sometimes you just sort of have to follow the path and do the successive multiplications. 2 times 2 is 4, times 2 is 8. So you notice that neither one of them is 6. This is not 3 times 2, this is not 2 times 3. And moreover, they're different results. So the exponent is not usually commutative. There are some exceptions, which you'll probably discover as we go along. Let's look at a couple of other examples. Let's take a look at 5 to the 4th power. Again, no special name for the 4th power, just call it 5 to the 4th power. Let me just briefly show you some symbolism that might occur in the future. If I don't have available to me Microsoft Word or some other program where I can type exponents like this, there's an old symbolism for exponent that looks like this. 5 and then something called a caret, the up arrow, which is on any keyboard. No matter what word processing program you're in, you can always type this because it's on the standard keyboard. So that was an old way to write 5 to the 4th power before we had the computer power to write it like this. So I might have to come back to this, and if I do, I'll alert you to it. And it's possible you'll see it in some old textbook somewhere. But nowadays, we almost always see it like this. And what does it mean? The definition of exponent. We're going to multiply some 5s together. Only 5s. Exponents are all about the repeated multiplication of the same number. And how many 5s are we going to multiply? 4. Now this is certainly not 20. It is absolutely not 20. It's way bigger than 20, which gives you an indication of why they're called powers. They're very powerful. With just a 5 and a 4, we can represent a fairly big number. 5 times 5 times 5 times 5. Let's just go from left to right. Now, I'm going to use the benefit of my experience, just being on this earth for a long time and being involved in math for much of my life. I've kind of memorized this one. You don't have to, but certain things will come up enough so that you will kind of memorize them without even trying. This is actually 625. 5 to the 4th power has the value 625. You see how powerful that is with just a 5 and a 4. Well, 5 times 5 is, of course, 25. And then we multiply that by 5. 25 times 5 is 125. Again, that's maybe something you'll learn pretty quickly. 4 times 25 is 100. 5 times 25 is 25 more. So this is 125, and then times the 5. And if you don't believe me, you can try it out on paper using the multiplication algorithm. But this is 625. I want to make this point. In evaluating or working out 5 to the 4th power, we only performed 3 multiplications. Sometimes students will throw in an extra multiplication when they're not supposed to. We're multiplying 4 5s together, as I wrote out, 1, 2, 3, 4. But of course, we do 5 times 5, get 25, and that's 1 multiplication there. Then we only have 2 more for a total of 3. You're always doing 1 fewer multiplication. It's 1 fewer multiplication than the exponent. But that'll just become natural as you work your way through it. Let me ask you this question. Do you think 4 to the 5th power is going to be 625? Well, I told you earlier that the exponent symbolism is not in general commutative. Maybe if I think of it, I'll show you one exception to that before we're done today. But 4 to the 5th power is not 625. Notice once again, I can't repeat this enough. 5 to the 4th power is not 20, and 4 to the 5th power is not 20 either. And furthermore, 4 to the 5th power is not 625. Now, my calculation skills are going to be tested a little bit more this time than before, because I kind of knew 5 to the 4th already. I have not memorized 4 to the 5th. But let's work it out. 4 times 5, oops, 4 times 4 times 4 times 4 times 4. 1, 2, 3, 4, 5 4s. 5 4s multiplied together. The exponent tells you how many of these numbers to multiply together. And of course, we're going to only perform 4 multiplications. We've got 5 4s, but we do take care of those 2 and get 16. And now we've got 1, 2, 3 more, so a total of 4 multiplications. 16, now we're on this third 4. 16 times 4, you should be able to do that mentally. I try to encourage 5th graders, even though we don't usually learn multiplication facts up to the 16 times table, but a little quick distributive property, 4 times 10 plus 4 times 6, 40 plus 24, 64. 16 times 4 is 64. Now we move on, just keep track of the numbers you're multiplying. We move on to this 4. We now have to do 64 times 4. Well, distributive property is not that hard here either. 4 times 60 plus 4 times 4. 4 times 60 is 240. 4 times 4 is 16, 256. If you have to do it on paper, do it on paper. But this is 256. And we only have 1 more 4 to multiply together. This time, for the distributive property, I'm going to think of 250 times 4. Because I know that, and you should know that. What is 4 times 250? It's 1,000. And then you've got 4 times 6 for 24. So put them together, 1,024. Now, like I said, I didn't know exactly, I hadn't memorized what 5 to the 4th was, but I had a strong suspicion that it was going to be greater than 625. You know, and you look at this, and as a 5th grader, you're not sure, because, you know, you got 5 to the 4th power, 4 to the 5th power. You know, the 5 went down to a 4, this 4 went up to a 5, so they kind of balance, so how would it work out? Which one would be greater? I knew they wouldn't be equal. As it turns out, the 4 to the 5th power is bigger, and that's generally going to be the case. And again, it goes back to the fact that this is powerful. Yes, we're multiplying 4s together rather than 5s. So that's the fact that we're multiplying 4s kind of indicates, you know, going lower, but we're multiplying it by an extra 4, and that's powerful. So this 1,024 is significantly bigger than the 625 because of the power of exponents. Let's right now cover something so that nobody will ever make this mistake on a quiz. I've had, through the years, every time I first quiz on exponents, a good amount of students make the same mistake with something like this. Let's see if we can all agree right now that we will not make this mistake. Now, it's natural. There's nothing wrong with you if you look at that and think that it's 7. But it's not 7. And if you say that that's 7, you're making the same mistake that you make when you think that 3 to the 2 power is 6, which it isn't. Or 2 to the 3rd power is 6, which it isn't. It's the same mistake. What does 1 to the 7th power mean? It means 1. Let me use a calculator. 1 times 1 times 1 times 1 times 1 times 1 times 1. So the calculator was my fingers to keep track of how many 1s I was multiplying together. There's the 7. That's not 7, it's 1. 1 to the 7th power is 1. I'm not going to write out all those, but you can picture them. 1 times 1 times 1. 7 of them. In fact, what is 1 to the 99th power? Not 99. Once again, it is exactly 1. 1 to a power is 1. Well, in our number system, there's another special number. How about 0? Is that 3? Is 0 to the third power 3? 1 to the third power is 3. I don't know. No! 1 to the third power is... 1 to the third power is 1. See? I did it. It's easy to make that mistake. Don't you do that. Okay, now here, I guess, I kind of didn't see this coming. I should have thought about it. When you've got 0 to a power, the wrong way to look at it kind of works, even though it's the wrong way to look at it. 0 times 3 is 0. That is the answer, but what? Well, what it means is 0 times 0 times 0, and that, of course, is 0. But don't let that one fool you. That's kind of an exception to that rule of, doing this times this. It happens to work with 0. Notice it doesn't work with 1. 1 to the 7th is not 1 times 7. It's 1. 0 to the third happens to be 0, but it's just because no matter how many zeros you multiply, you get 0. All right. I want to look at another cool one right now, a special one. We didn't talk about this yet, but if you raise a number to the 1 power, you get the number. It's kind of hard to fit into the definition. Exponents are repeated multiplication. You take a number and you multiply a certain number of them together. Well, we're not really multiplying any 10s together here, because the exponent's 1. And this turns out to be what you would expect it to be. And again, it's kind of an exception to that rule. 10 times 1 is 10, but that's not why here. I'd actually have to get into an extension of exponents that I cover in 7th and 8th grade. Like anything in math, we're learning simple exponents here. We're going to expand our knowledge of exponents, and when we do that, I'll be able to easily convince you that 10 to the 1 power needs to be 10. And it kind of makes sense here anyway. We're going to multiply 1 10. Okay, well, that's 2 10s. So we're just going to multiply 1 10. Well, we're not really multiplying it, but you get the idea. Now, 10 is a special number in our number system. Our number system is called base 10. There are 10 digits. 0 up to 9, that's 10 digits. And when we write this, a 1 and a 0, that's the first 2-digit number. That's the base of our number system. The first whole number that we cannot write with a single digit. That's the base. All right. So 10 is a special number. There are many examples of this. If you multiply 4 times 10, you get 40. And then also, if you multiply 4 times 100, you get 400. Just tack on those zeros. You've experienced that with multiplication. Well, multiplying by 10 is easy. Multiplying by powers of 10 is also easy, because all the places of our number system each place is a power of 10, as you'll see in a moment. Let's consider 10 to the 2 power. Now, please understand, I'm calling these the powers of 10. Every time I'm going to write the base here of 10, and then the exponent is the power. These are the powers of 10. 10 to the 1 is 10. What's 10 to the 2? You know. Figure it out. It's not 20. It's 100. 10 times 10, multiply 2 10s together and get 100. And very soon you should see a pattern developing. 10 to the 3rd power. What does that mean? The 3 tells us to multiply 3 10s together. 10 times 10 times 10. And of course that's 1,000. So look over here and look at the result and see if you can notice a pattern. I'll do a couple of more. 10 to the 4th power. Now, I'll give you a little hint here about the pattern. You don't have to multiply. You don't have to do all these multiplications. When we had 5 to the 4th or 4 to the 5th, you got to grind that out and multiply those together. If you were doing, say, 7 to the 6th power, it's a lot of multiplication you have to do there, or you use a calculator. But you can immediately write down these answers. That's the pattern. 10 to the 4th means 10 times 10 times 10 times 10. 4 tens multiplied together. Of course, it's not 40. It is 10,000. 10 times 10 is 100. 100 times 10 is 1,000. 1,000 times 10 is 10,000. One more, and then I'll ask you for the pattern. 10 to the 5th is 10 times 10 times 10 times 10 times 10. 1, 2, 3, 4, 5. Now, here's a little shortcut. We just found 10 to the 4th. We know that these 4 tens multiply to 10,000. Don't reinvent the wheel. Use what we just did. All right? And 10,000 times 10 is 100,000. Make sure you can see that there. 100,000. Now, in a previous video, I did things like 20 times 30. Talked about that easy algorithm where you just multiply, to do 20 times 30. 2 times 3 is 6. And then you got a 0 in the 20, a 0 in the 30, so you tack on 2 zeros to the 6. 20 times 30 is 600. Well, this is the same algorithm, except we're multiplying ones. So everything's going to start with a 1 and be followed by zeros, right? 10 times 10 times 10. 1 times 1 times 1 is 1, and then you have 1, 2, 3, 1, 2, 3. 3 zeros. Okay, but where else does the 3 appear? Well, it's right there. That's the pattern. When you raise 10 to a power, the result is a 1 followed by zeros. And how many zeros? The same as the power. The same as the exponent. This only works for 10, but it's beautiful. It's a wonderful result that you should be totally comfortable with. Right? So, just to get crazy, let's talk about a Googol. That's right, a Googol. I'll be right back. Going to do some erasing. You're going to come to realize as you go through school or just go through life and learn about certain topics, there are legends. What I'm about to tell you might be a legend. I did read about it somewhere years ago. It's a story about how this idea of a Googol came about. And it goes something like this. And how much of it is true or not, I'm not sure. But I think it's at least a lot of it is true. There was a mathematician, a college professor. I think it was in the 1940s, the mid-20th century. And this mathematician, the story goes, had a young child, nephew, niece with him, and they were just kind of talking about things. And whether it was the child or the math professor himself who came up with the idea, what about a 1 followed by 100 zeros? Why 100? Well, it's a nice round number. It's a nice number in our number system. Could have been a 1 followed by 99 zeros, which would be smaller, a 1 followed by 101 zeros, which would be bigger, but it's sort of a nice round number. A 1 followed by 100 zeros. Now, if you want, try a little experiment. Take a timer on your phone or some kind of stopwatch type of timer. Get a piece of paper, start the stopwatch, start the timer going, write a 1, and then 100 zeros. You got to count the zeros as you go. You got to come up with some method to do that. And see how long it takes you. I'm not going to take up our time right now doing it, but it doesn't take very long. And, okay, there it is. Big, long number. You can write it in, I think, maybe a minute. Under 2 minutes, you could write this number out. A 1 followed by 100 zeros. Of course, According to what we're learning now about exponents, this is a 1 followed by 100 zeros, right? Imagine 10 times 10 times 10 times 10, 100 of them. That would be a 1 followed by 100 zeros. So this is a Googol, 10 to the 100th power. And this story, this famous story about the Googol, the mathematician asked the child, well, what should we call this? And the child supposedly came up with this name, Googol. Now, when people have thought about this and written about this since, they say, well, you've got 3 O's, right? 2 O's here, the O here, and they kind of remind us of all those zeros. So even though it's a made-up name, it's just a totally made-up name, it kind of makes sense. And by the way, you might have found this video by Googling, and probably not, I probably gave you the link, but someday, if you don't have a link and you want to watch Mr. LaBeouf videos through some sort of Googling, this is the name of that giant tech company that has the search engine, and of course it's got a lot of other products that we use in school, like the Google Classroom. When the people who founded this company, Googol, they took it from this. They changed the spelling. They wanted to have their own unique spelling of it. But they also wanted to convey the idea of bigness. You know, what is Google all about? Well, the search engine searches the enormity, the giant amount of information that's out on the World Wide Web, the internet, and it searches through that. So they wanted their company name to have this idea of bigness. So that's a little lesson there on Google and Google. One quick point. This is not a Googol. This, of course, is 1. If you want a 1 followed by 100 zeros, it has to be 10 to the 100th power. I told you a moment ago, you could write out 10 to the 100th power, work out all the multiplications, realizing it's a 1 followed by 100 zeros, and do that in a minute. Well, I will not ask you to do that. I won't ask myself to do that. I know what it means. It means multiply 100 9s together. Now, that's a huge number. A Googol is a huge number. This is less. That's intuitive. That's obvious, right? 9 to the 100th is less than 10 to the 100th. It's probably considerably less. This is a nightmare to calculate. Even a calculator can't do it. A calculator can only approximate because there aren't enough digits to display it. Okay? Just wanted to make that little point. And do I want to leave you with this? I think I will. And if I don't explain why what I'm about to say is true soon, if I don't explain it in a video soon or in class, please remind me to. I don't want to forget to do this. But let me make the statement. It's a bold, counterintuitive statement. Intuitive, counterintuitive. The word intuitive means kind of like what the human brain naturally would assume without really thinking about it, just sort of your initial reaction, intuitive. It's intuitive that 7 to the 1 would be 7. Okay, that's an example. I used that example earlier, I think. Something to the 1 power is the number. So that's intuitive. There are things in math that are not intuitive, and part of my job is to get you to see what is intuitive and what is counterintuitive. If something's not intuitive, it's counterintuitive. It goes against what we would think. So let's consider this number Googol, which this is a word which means, everyone agrees now that this word means a 1 followed by 100 zeros, and 10 to the 100 power is that, right? And I suggested earlier you could actually write the 1 followed by 100 zeros in a minute or so. Probably under 2 minutes easily. So here's the counterintuitive statement. That quantity, you know, numbers represent quantities. When I write the symbol for 5, it means this many things, right? So a Googol is a quantity, but how big is it? Okay, here's the statement. Brace yourself for it. A Googol, the quantity, how much it is a greater quantity than all the atoms in the known universe. Now, I did a little research on the internet once regarding stars and atoms and galaxies, and I convinced myself. I want to leave that thought with you. I'm absolutely convinced it's right. I've seen it in many sources, and I've actually convinced myself that it's right. I want to do that for you next time or very soon. But understand, you know, atoms are tiny, tiny. Even with a standard microscope, you cannot see them. There is something called an electron microscope that can kind of get a sense of an image of an atom. But in a grain of sand, there are many, many, many atoms. One grain of sand. I don't really know. How many? Trillions, maybe? I don't know. A lot of atoms in a grain of sand. In my God, there are many, many, many atoms. The sun. Okay? Sun, way bigger than anything else in the solar system. That's part of the understanding of how you can understand that a Googol is a greater quantity than all the atoms in the known universe. There are, scientists tell us, hundreds of billions of stars in our galaxy. Our galaxy, I think, is typical, average-sized galaxy. Hundreds of billions of galaxies. So try to wrap your head around that. Our sun, a star, is one of hundreds of billions in the Milky Way galaxy. The Milky Way galaxy is one of hundreds of billions of galaxies. And try to imagine, I mean, you have a concept right now of how small an atom is. How many atoms are in the sun? Big number. But this number, a Googol, is bigger than all of the atoms in our sun, all the atoms in our galaxy, and also all the atoms in the entire known universe, which is hundreds of billions of galaxies. Counterintuitive. When I first heard it, really? Let me try to convince you of that next time. But for now, the key takeaway here is exponents. It's a piece of symbolism. It's a very simple piece of symbolism, but it's your obligation to learn it well, learn it forever. And let me close with this final statement. 3 to the 2 power is not 6. Please don't tell me that it is. Or maybe for fun just once. We don't want to repeat a math lie, do we? 3 to the 2 power does not equal 6. Thanks for listening. See you later.